Hey yo, what's up? Good morning, guys. I hope you're having a nice day. So, our topic for today is about the manual radar plotting. I am Lindio Leo Evan Majunero with my teammates Ogok Giancarlo, Montehermoso Archie, and Bulawan Jun Ronel. Will be group 10. We'll talk about or discuss about manual radar plotting. So, let's begin. Learning intended outcomes. At the end of the discussion, the students shall be able to plot in radar manually, know the CPA of the targets and the other parts like the speed and course of the targets by radar plotting. So, radar plotting is an alternative for ARPA. ARPA means a automatic radar plotting aids, and thus it will be handy when ARPA is not working. So as we as karon kanang high tech naman ta so that natay mga electronic devices like ARPA like this, and pananglitan maguba ang ARPA or not functioning. So we will do the manual thing, mag radar plotting siya gamit ang radar plotting sheet. So let us assume a very realistic situation. ARPA of one of your radar stop working in the mid-sea. Of course, the vessel is not complying with the SALAS. So, wag siya nilihok, then naguba mo to. Then the master will report the fact to the company, and the company will seek dispensation from the flag to sail and arrive at next port without working ARPA function of the radar. And
We aim to get all information that ARPA can give. These pieces of information are CPA and tcpa of targets. So CPA means the closest point of approach of the paint, while tcpa means the predicted time of closest point of approach. Second is course and speed of the target. This is how radar plotting sheet looks like. So as you can see in the picture. When we say the target on the radar, we take the bearing and range of the target and note down the time of observation. Let us say we noted the following bearing or range of a target at 18 hours LT or the local time. So target A, the time is 18 hours with a range of 8.0 nautical miles with a bearing of 60 degrees. Let us plot this on the radar plotting sheet. This point of first observation is named point O. So as you can see in the radar, the point O is located in 60 degree bearing in the range of 8.0 nautical miles. Now after some interval, take the second and third set of observation of the target and plot it on the radar plotting sheet. So target A, the time is 18 hours with a range of 8.0 nautical miles with a bearing of 60 degree. And second is 18.6 8 hours. So with a range of 7.0 nautical miles with a bearing of 59 degree. And third is 18.12 hours with a range of 6.0 nautical miles with a bearing of 57 degrees. So the next topic will be discussed by General Bulawan.
Place on radar plotting sheet and extend the line joining all 3 points. Name the points of last observation as point A. So, this is the line of relative approach of the target towards our vessel, which we have assumed at the center of the sheet. So, now for CPA, we need to find the closest point of the line approach to the center. To do that, just draw a line perpendicular at the line of approach and measure the distance of this line from the scale in the radar plotting sheet. The CPE here is around 0.8 nm or nautical mile. To calculate TCPA, we need to calculate the time required to reach at point C, considering it took 12 minutes to cover distance OA. To do that measure the distance CA, and that would be 5.8 nautical mile in this case. Now, with simple mathematics calculate, the time at the target would take to cover 5.8 nautical mile with the relative approach speed. This would be the tcpa. In this case, the tcpa would be 35 minutes at 18:47 hours LT or local time. 2 nautical mile is the OA. Then 5 nautical mile is the CA. In 12 minutes, and the CA is question mark. To solve this, TCPA equals 12 times multiplied by 5.8 divide 2 minutes. So the answer is 34.8 minutes or 35 minutes. Course and speed of targets by radar plotting. Next is to find the course and speed of the target. To find that, from point O, draw your course in opposite direction and cut the distance your ship has traveled for the time period of OA. 12 minutes in this case. Let us say your course is 0.45 degrees and speed is 12 knots. In 12 minutes, your ship with speed 12 knots will travel 2.4 nautical mile SO from point O. Draw a line in direction 2 to 5 degrees and measuring 2.4 nm. Name this point as W, such as WO is your course.
So now for CPA, we need to find the closest point of the line of approach to the center. To do that, just draw a line perpendicular to the line of approach and measure the distance of this line from the scale in the radar plotting sheet. So here's an example. So the center in there is the CPA, or the closest point of approach. So the CPA here is around 0.8 nautical miles. To calculate the CPA, or time closest point of approach, we just need to calculate the time required to reach at point C, considering it took 12 minutes to cover distance OA. So to do that, measure the distance CA, and that will be 5.8 nautical miles in this case. Now, with simple mathematics calculate the time the target will be take to cover 5.8 nautical miles with the relative approach speed. This will be the TCPA in this case. So the TCPA will be 35 minutes at 18:47 hours latitude. So in 2 nautical miles, it has a minutes of 12 minutes. So we're gonna solve the minutes and 5.8 nautical miles of CA. So solution is TCPA, or time closest point of approach, equal 12 times 5.8, and you're gonna divide it by 2 so that we can get the minutes. So the result in there is 34.8 minutes. So 34.8 minutes, we're gonna convert it, then the result will 35 minutes. So course and speed of targets by radar plotting. Next is to find the course and speed of the target. To find that, from point O, draw your course in opposite direction and cut the distance your ship has traveled
traveled for the time period of OA, and 12 minutes in this case. So let us say your course is 045 degrees and speed is 12 knots. In 12 minutes, your ship will, with speed 12 knots, will travel 2.4 nautical miles. SO. From point 0 or O, draw a line in direction 225 degrees and measure 2.4 nautical miles. Name this point as W, such that WO is your course. So this is the result of our plotting. So now join W and A. And W and A is the course and speed of the target vessel. So measure the distance WA. This is the distance covered by the target in 12 minutes. With simple mathematics, calculate the distance it will travel in 60 minutes to get the speed. So the result will be this. In this case, the course of the target is 300 degrees and speed is 7 knots. WA measures 1.4 nautical miles. And that's all.
Hello and welcome to today's video where I'm going to be showing you how to complete a radar plot. So for radar plotting, the first thing we need is the plotting sheet, which consists of the radar screen and a scale along the side. We're going to determine a couple of things in advance. We're going to be doing a 12-minute plot, and our own vessel is going to be doing 10 knots going 000, so due north. This means our own vector is going to be 2 miles long as measured on our scale, because in 12 minutes at 10 knots we would have travelled 2 miles. And then we're going to place it in the centre of the screen, pointing due north. This just represents our own true vector. The screen itself, we're going to take, it's roughly 6 miles. It's give or take a little bit just because of the dimensions of the screen though. But yeah, we're going to call this a 6-mile plot as well. So, as soon as we receive our first echo, we can't really determine much. All we know is the range and bearing of the target vessel. We need to continue to monitor to find more information. Then we find the next point. Again, we haven't quite got enough here. We're really working on scanty information at the moment. There's not enough to complete the plot. And then finally, 12 minutes after the initial plot, we get our third plot. So each of these plots is 6 minutes apart. The full range is 12 minutes, as we previously said. So all we're going to do to immediately find the CPA is we can join a line straight through the middle. And in this particular example, the closest point of approach is 0. If we do nothing, there will be a collision. Now, to find out how long until that collision, we need to measure a couple of distances. This first distance here, we need to find out how far the target vessel has travelled in the 12 minutes we've been plotting it. All we do, transpose that onto the scale, and we see in the last 12 minutes, target vessel has moved 1.5 miles relative to us. Then, we need to find the distance that the target vessel has got to go from its final position until it reaches us. Again, we're going to transpose this onto the side scale and measure up to find it's about 3.3 miles. To work out how long it's going to take to travel that, we need to do a ratio between these. The ratio of 3.3 to 1.5 will be the same as the time to go to 12. And we simply lay it out like this. All we do is move the 12 to the other side, simple algebra here, to find the time to the closest point of approach, and running that through the calculator, rounding off to the nearest minute, we get 26 minutes. We can start writing these down the side. So our CPA, as we've said, is 0, and our time to the closest point of approach is 26 minutes. There's a couple more bits of information we need. The next ones are going to be the target vessel's course and speed. This is where vectors start to come into play. what we're going to do is we're going to start to label up parts of the diagram. We're going to call the first plot we received O. Reason for this is it's the original plot. It's the original position the vessel was in when we first saw it. The next point we're going to call A, because at the time of this plot, that is the actual position of the vessel. That's the last plot we received. They are actually there. Then we're looking for the other point, W. Now W to me doesn't really stand for anything apart from labeling the vectors themselves. And to find W, what we want to do is move our own vector pointing towards the O. And then the bottom of our vector becomes the W. The way to remember this is W to O is the way of your own vessel. W is going to be the point where we're doing all our vectors from, and O being the original position of the target vessel. To find this course and speed of the other vessel, we simply want the vector going from W to A. And we label that WA, which is way of another vessel. And simply the vector joins the two together. Now, as we know from maths, vectors are a component of distance and bearing, or speed and bearing. Otherwise it would just be a measurement, but no, a vector contains more information. So to find out the target's course, we'll transpose that vector to the middle, extend it out to the edge, and we can simply read off the edge of the diagram to determine their course. In this case it's 303 degrees. To find their speed, all we're going to do is measure the length of that vector, and we find it's about 1.1 miles. They've done that 1.1 miles in 12 minutes. Now, of course, to get 12 minutes to an hour, you multiply by 5, so we times both by 5 to get 5.5 knots. Now we've found their course and speed. The next things we want to find are the bearing at the closest point of approach and the aspect. Now, in this particular example, where the closest point of approach is 0, there is no bearing, so that one is actually irrelevant. If the closest point of approach, otherwise it would just be a measurement, but no, a vector contains more information. So to find out the target's course, we'll transpose that vector to the middle, extend it out to the edge, and we can simply read off the edge of the diagram to determine their course. In this case it's 303 degrees. To find their speed, all we're going to do is measure the length of that vector, and we find it's about 1.1 miles. They've done that 1.1 miles in 12 minutes. Now, of course, to get 12 minutes to an hour, you multiply by 5, so we times both by 5 to get 5.5 knots. Now we've found their course and speed. The next things we want to find are the bearing at the closest point of approach and the aspect. Now, in this particular example, where the closest point of approach is 0, there is no bearing, so that one is actually irrelevant. If the closest point of approach was, say, a mile, then we'd want the bearing to where the vessel would be when they were 1 mile off us. We will cover that when we look at a more advanced plot. And the final thing we want is the aspect. Now, the aspect's a little bit tricky because of all the workings out we've done on the screen so far. We actually want to change things up a little bit. And all we're going to do is move the target vessel's vector onto their actual position. Now, if you look at this, this looks actually exactly like a normal radar screen, where we've got a relative motion plot, where relative to us all the dots are moving, but the vectors are true vectors. We've got our own true vector and the target vessel's true vector. Now, the aspect is going to be the bearing we are from the target vessel. So to find that, all we're looking for is the angle between their heading, or their course, and the bearing to us. And we can either measure that directly from this position, or we can transpose their heading to the centre and extend the lines out where we've got a nice gauge of degrees around the edge, and all we want is the difference between these. Now, you'll note that the bottom line doesn't quite go through 225 where it should. This is just because of the dimensions of my diagram, but we know it's the reciprocal of the bearing we've been detecting the target, so it should actually be 225. So to find this out, all we do is 303 minus 225, and we get 78 degrees. Now we know we're on their port side, So we're just going to label that as red 78 degrees. Now, after all that, we've completed the plot. Completing the plot simply means finding the closest point of approach, time to the closest point of approach, target vessel's course and speed, their bearing when they're at the closest point of approach, and their aspect. In other diagrams it would be more difficult to find these, and we might have a CPA that's not quite 0. Now, to confirm all this, let's just swap it out from a radar plot and look at the overview